Hi, this is Kate and we're graphing linear inequalities. Claire wants to order some CDs and DVDs from a website. On average, CDs cost $12 each and DVDs cost $18 each. Shipping will cost $2. Claire can spend no more than $200. So just to start to wrap our heads around this problem, decide whether Claire is able to order 10 CDs and 5 DVDs. If she places that order, she'll spend more than $200. To find the cost of 10 CDs, we'll multiply 10 by 12. And to find the cost of 5 DVDs, we'll multiply 5 by 18. That's how much each one costs. And then we have to add on $2 for shipping. So she'll spend $120 on CDs, $90 on DVDs, and the $2 on shipping, which altogether comes to $212. This is more than she wants to spend. So which combination of CDs and DVDs is an example of an order that will add up to less than $200, including shipping? The only order less than $200 is 12 CDs and 2 DVDs. If we find the cost of each order, like this, choice C is the only one that adds up to less than $200. So Claire thinks to herself, it would be nice to have a picture of this situation so she could easily see if certain combinations of CDs and DVDs are within her budget. So she decides to make a graph. She'll use X for the number of CDs she orders and Y for the number of DVDs. Which inequality fits this situation, where the amount of money she spends on her order is less than or equal to $200? Choice A represents the situation. She'll spend $12 for each CD, $18 for each DVD, and then $2 for shipping. She wants that amount to add up to be less than or equal to $200. So in order to make a graph, she thinks, well, why don't I get this into y is less than or equal to mx plus b form? This will tell me all the combinations of CDs and DVDs where the order will equal $200. So help her out by doing a little algebra. You might want a pencil and paper and put this inequality to y less than or equal to mx plus b form. The equivalent inequality is choice B. To get y by itself, first we'll subtract 2 from both sides, then subtract 12x from both sides. Finally, divide both sides by 18. Once we reduce those fractions, we end up with y is less than or equal to negative 2/3 x plus 11. Look at the two choices carefully. Which graph represents this equation? Choice A represents this equation because it has a y-intercept of positive 11 and a slope of negative 2/3. Now Claire can easily look at this graph and see, for example, if she purchases 12 CDs and 3 DVDs, she'll spend exactly $200. If she purchases fewer than that, only 6 CDs and 5 DVDs, she'll be under the line. She'll spend less than $200. But if she tried to order 9 CDs and 10 DVDs, that would be too much. She's over the line, spending more than $200. The graph of the inequality should reflect all the xy pairs that make the inequality true. So which graph represents y is less than or equal to negative 2/3 x plus 11? This is going to be the same graph, because it's the same equation, we just changed it with a little algebra, as 12x plus 18y plus 2 is less than or equal to $200. Which graph reflects our situation? That would be choice B. All the xy pairs underneath the line Reflect an order that adds up to less than $200. Now I'll show you a procedure for graphing any linear inequality. We're going to start with a pretty simple example. First, read this inequality and translate it into words. This inequality can be read as y is greater than twice x minus 5. Less than would be facing the other direction, and greater than or equal to would have the little bar underneath to indicate also equals to. Now test the points in the inequality and figure out which point x comma y makes this inequality true. The only point that makes it true is 6, 10. When y is 10 and x is 6, we have that 10 is greater than 2 times 6 minus 5. 2 times 6 is 12, so this inequality is saying 10 is greater than 7, which is a true statement. You may be wondering about choice B. If we substitute in a 6 for x and a 7 for y, what we're saying is that 7 is greater than 12 minus 5, or 7 is greater than 7. This is a false statement. If it were greater than or equal to, it would be true, but since it's strictly greater than, it's false. And then choice A winds up saying that 3 is greater than 7, which is also a false statement. So choice C is the only one that makes it true. So our graph should reflect the fact that 2 of these points are false and 1 of them is true. 6, 3 and 6, 7 do not make the inequality true, but 6, 10 does. So we could hunt and peck and find a whole bunch of points that make our statement false, and also find a whole bunch of points that make our statement true. And this is kind of a picture of which points on the plane make it true and which points don't. However, it's much quicker and more convenient if we just graph the boundary of these two regions. This is the line where y equals 2x minus 5. And of course, you guys already know how to graph a line. This is no trouble at all. So instead of putting a whole bunch of symbols like this for each point, we're just going to graph the line and then shade the side where it's true. This shows all the xy pairs that make this inequality true. Now there's one little problem with our graph here, in that we haven't thought how to differentiate between greater than and greater than or equal to. If we were graphing all the points that made y greater than or equal to 2x minus 5, we would be good. We would be done, because we'd want to include the line in our graph of the stuff that makes it true. For greater than or equal to, we use a solid line. However, the points that lie along this blue line don't make our inequality true. We don't want to include the points that are on the line. So we indicate that with a dashed line. For y is strictly greater than 2x minus 5, we'll use a dashed line to indicate that we're not including the line itself, only the shaded part that's to the left of the line. So to recap, in order to graph an inequality, we'll first graph the boundary line. This is where the two sides of the inequality would be equal. Then decide which side of the line to shade by testing some xy pairs within the inequality to see where it's true. Let's illustrate this with an example. Negative 1/2 x plus 3 is greater than or equal to y. So first we'll want to graph the boundary line, where negative 1/2 x plus 3 is equal to y. Can you choose the graph that would correspond with this boundary? Choice A is the correct graph because it has a y-intercept of positive 3 and a slope of negative 1/2. We choose the solid line because our inequality is greater than or equal to. If it was strictly greater than, we would have chosen the dashed line, choice C. So we've graphed the correct boundary line. Now we need to decide which side of this line has the points that'll make our inequality true. So pick a few points, test them out in the inequality, get a feel for where it's true, and then indicate which side of the line we should shade. If we test a few points, we can see that the points underneath the line make this inequality true. For example, If we try the origin, 0, 0, so plugging in a 0 for x and a 0 for y. Anything times 0 is 0, and 0 plus 3 is 3. 3 is greater than or equal to 0. That's a true statement. So that's the side of the line that makes the inequality true. That's what we're going to shade. If we chose a point on the other side, for example 8, 8, and plug that in, negative 1/2 times 8 is negative 4, and we end up with negative 1 is greater than or equal to 8. That's a false statement, so we know that we don't want to shade that side of the line. This is Kate, and we've been graphing linear inequalities.